Hello, we're back for our last lecture of the semester. I want to continue with cosmology, and we were talking about evidence for the Big Bang, this background radiation, the cosmic background radiation, the 3 Kelvin cosmic background radiation discovered by Penzias and Wilson. Good to know them for the final. And some more evidence for the Big Bang. You see this little thing, that looks like an egg? It's not an egg. It's not an Easter egg, even though I know it's about Easter time. This is a full view in microwaves, converted to visible light of the whole universe, of the sky all around us, kind of then opened up. And it shows there was another prediction. Another prediction is if there were a Big Bang and galaxies started to form afterward, stars form first, then galaxies, that there should be regions of the sky where the temperature, this 2.735 Kelvin, should be slightly unevenness. And we had a spacecraft called the WMAP, you're not going to have to know that, that took this picture. And there are places where it's a little bit cooler and a little bit warmer, a little cooler here, a little bit warmer, exactly what we would have thought if the galaxies formed shortly after the Big Bang, that there should be slight variations in this 2.735 Kelvin. Now, it's almost this temperature all around, but if there's slight variations, and that's what this represents, some more evidence for the Big Bang. Now, let's talk about this. The epoch of inflation. Alan Guth proposed this, and the idea is this, that even though the universe, there's slight variations in temperature all around, that the universe seems to be pretty uniform everywhere. It seems to be the same. And the idea is this, that the universe expanded faster than light within the first second that the universe began. When the first second that the universe began, when it was less than a second old, there was a rapid expansion of the universe where it got very, very big, very quickly. It went faster than light. And you may say, how does the universe go faster than light? Well, at this point, there were no laws. If the laws of nature didn't exist, especially the law that says you can't go faster than light, well, you can do what you want. If there are no laws, you do what you want. And, you shouldn't necessarily do everything you want, but that's what happened. If there are no laws, then the nature of the universe is the universe can do what it wants. So the universe kept its uniformity in all directions, everywhere, by just expanding very quickly. So it had its properties, and it got really big, and one side of the universe, one part of the universe is now pretty much the same as the other part. And we thought at this time that all the forces that we have talked about, there's the gravity and the electromagnetic force, and there's a strong force, there's even a weak electromagnetic, or weak nuclear force, I should say, and the strong nuclear force, that they were all one force, one super force. It's called the grand unified theory. And that what happened was gravity splits off when it was less than a second old. Gravity kind of separated out from these forces, and this universe expanded very rapidly. It's called the inflation. Just know what is inflation, proposed by Guth. It's inflation, proposed by Guth, that the universe expanded very, very rapidly, very quickly, when it was less than a second old. Good to know. It's good to know Guth. It's good to know inflation. Now, based on, I'm not going to show this. It gets a little convoluted, this picture, but I do want to mention this. Based on recent findings and the Hubble constant, I'd like you to know the age of the universe. What we think the age of the universe is. It changes. Every time we find out something new, it might change by a little bit, but as far as right now, the age of the universe, we think, since the universe began, 13.7 billion years. It's the age of the universe. It's good to know. Now, you don't really have to know this, but they say that the universe is about 156 billion light years in diameter now. You may say, well, wait a second, if the universe is 13.7 billion years old, and maybe we could see out to 13 billion light years and seeing things that far back, how come the universe is not something like, 27 billion light years in diameter? Well, let's think about this. If we see something 13 billion light years away, a galaxy being born, a quasar, because of the expansion, where we're seeing it the way it looked 13 billion years ago. That's where it was. Is it there now? No. Over the last 13 billion years, it's moved much, much farther from us. The universe has expanded. Space has expanded. So the universe is much bigger than even appears to the naked eye. Even beyond your cosmic horizon, there's universe there. but the light hasn't had time to reach us. So this is kind of a little weird. I mean, it gets a little weird here. Now, if you think that gets weird, gee, this is, okay, don't write anything down here. I'm going to go through this quickly. I need to get to some stuff, but this is some old ideas. The fate of the universe. They think, okay, what is the universe going to do? And again, I'm not going to test you on this. They say, okay, the universe might expand forever. All right, could do that. Or it might stop expanding and start contracting. Or it might do neither. It might expand until for an infinite amount of time and slowly stop. It's like this. It's like, okay, expanding forever, maybe you can imagine that. Stop expanding and start contracting, well, you can almost imagine that. It's like blowing up a balloon almost and then letting it deflate. But what's in the middle? What about this? If I say, okay, there's a wall, and keep cutting your distance in half to that wall. So let's say you start at 6 feet from the wall, then you get to 3 feet from the wall, then 1.5 feet, so on. Are you ever going to get to the wall? No. You're going to get close, but you're not going to get to the wall. So the universe might stop expanding after an infinite amount of time. That's like doing neither. Again, do not write this down. What they thought that this might depend on how much mass is in the universe. If there's enough mass in the universe, maybe it'll stop expanding and start contracting, and they would call that like the big crunch. Or if there's not enough mass in the universe, it'll expand forever. And if there's just enough mass, known as the critical mass, maybe it'll stop expanding after an infinite amount of time. Well, that was the old idea. So, and then they talked about geometries of space-time, of the 3 dimensions of space. Is that curved into a 4th dimension? Don't worry about that. This is the geometries of space-time. Gets a little strange where, depending on the geometry of space-time, 2 parallel beams might stay parallel, they might converge, they might diverge. Don't worry about that. And certainly don't worry about the space slug. This thing should go. I mean, this is old news, the space slug. And don't write that down. But here's something else. Something called dark matter. Dark matter, you may have heard of it. And they think the universe is a large part dark matter now. Maybe. It's matter or mass that doesn't emit or reflect any observable EMR, called dark matter. Now, you might think if astronomers call something dark matter, astronomers know, these astrophysicists, dark matter, they know something we don't. Well, you know what it means? It means they don't know anything we don't when it comes to this. That's why they call it dark. Dark means they don't know. And if they don't know, they call something dark. It's not some special thing where we're in the dark and they're illuminated, they know something. No, they don't know. But dark matter is matter that doesn't emit or reflect any observable EMR. Nobody knows what it is. They think maybe black holes can account for that dark matter. It could be these things called weakly interacting massive particles, or WIMPs. It could be neutrinos. Maybe things we don't even know. But we've detected gravitational warping of space and time by stuff we're not seeing. We're seeing sometimes galaxies brighten. Some things between galaxies end up, light from one galaxy to us, it appears to brighten as if something is in the way, warping space and time, kind of making a gravitational lens that we don't see. Now, some astrophysicists, or I should say some theoretical physicists like Michio Kaku, who's great, he thinks, okay, there's probably dark matter there, but that there might be other universes out there, that we might live in what is called a multiverse, that our universe might just be one of an infinite number of universes in other dimensions. There could be other universes in the room with you that you can't get to. That's crazy. It sounds crazy, but who knows? We have some of the most incredible minds on the earth saying things like this. It's not somebody like on YouTube just posting their video about, the earth's flat because of this and watch this video. No, it's not that. Michio Kaku and other people like Brian Greene, these are people that actually went to school, that people that have read things about science, and not some of these other people. So, this is an idea. A lot of these theoretical physicists, most of the mass in the universe seems to be dark matter. Now, also some people think that the gravity from other universes might be seeping through dimensions to get to us. Now, that is weird stuff. But actually, some of the greatest minds on the earth are saying things like this. So I listen to these people. And now, they'll be the first to say they might be wrong. But, you know, if Einstein's going to tell me something, I'm listening. If Neil deGrasse Tyson's going to say something to me, I'm listening. If Michio Kaku or Brian Greene, if they say something to me, you know, I'm listening. So, they're the first. Again, they're the first to admit that if the evidence doesn't come up, then yeah, they could be wrong. But I go by what those guys say before anybody else. Now, let's talk about this dark energy. Now, again, when you look at this, don't think that someone knows what they're talking about. They don't know what they're talking about. Well, they know what they're talking about, but they're not sure what this is. Well, but here's what they think it is, and they're not sure why, though. It appears to be an anti-gravity force that is accelerating the expansion of space-time. Now, this is weird. We said the universe is expanding. Space-time is expanding. There is some sort of property of space-time for when it expands. It actually gets more stretchy, and it expands even faster than it should. And no one understands this. It's like an anti-gravity force. And what do they call it? Dark energy. It appears to be an anti-gravity force that's accelerating the expansion of space-time. And they say this, because of this dark energy, if this is correct, now again, this is what they think that they're seeing here. That means that the universe, the space-time might stretch to the point in the future so much that you can go out and not even see any galaxies out there. I mean, for the most part, there's so much space between the galaxies, and the universe will get so big, all stars eventually will die and turn into heavier elements, and then you don't need, so there's not 100% recycling, and eventually it's going to be a heat death where the energy of the universe gets so dilute that the universe will be a cold, dark place. It's kind of depressing. But you don't have to worry about that. It's not for probably hundreds and hundreds and hundreds of billions of years. So we got some time. So this dark energy, appears to be this anti-gravity force. And you know what they also say it might be? It's like the same thing that might be responsible for inflation that Guth theorized about. That whatever accelerated the universe very quickly, very fast, within a second old, might be rearing its ugly head again. So this dark energy, we're not sure what it is. But, remember Einstein? He had proposed an anti-gravity force called the cosmological constant, later on saying it was the biggest blunder of his career, that was a mistake. Well, even though Einstein didn't propose it for the right reasons, even Einstein, when he's wrong, this is like an anti-gravity force. That was an anti-gravity force. Even Einstein, when he's wrong, in some way kind of turns out to be right. So the last picture I'm going to leave you with is this, Einstein. So again, even Einstein's mistakes might be monumental discoveries. So we'll probably talk again. I need to talk to you about things, but this is the last lecture. And I want to thank you for being in the class. Sorry it had to end this way. Maybe I'll see you for an Astronomy 12 or something at some point. If you liked Astronomy 3, try Astronomy 4 if you haven't taken it already. And good luck with everything. But I'm sure, after this video, we're gonna have our final and everything. But as far as videos, this may be the last. So take care of yourselves, and thanks for dealing with all this in this fashion. Bye.